Imagine for a moment that you could travel deep into the Earth, far below the ground we walk on every day. You would be embarking on a journey more incredible than any space mission, to a place more alien than the surface of Mars. Down there, in the very heart of our planet, lies a world of unimaginable heat and crushing pressure. It is a realm of solid iron, hotter than the surface of the sun, a sphere nearly the size of our moon, silently spinning within a sea of liquid metal. For centuries, this hidden world was a complete mystery, a subject of pure fantasy and speculation. But today, thanks to the brilliant ingenuity of science, we are beginning to pull back the curtain on the secrets of Earth's core. This journey of discovery is not one we make with drills or submarines, as the deepest we have ever managed to dig is a mere fraction of the way there. Instead, our explorers are waves of energy, born from the shudder of earthquakes that travel right through the planet. These waves act as our eyes and ears, carrying back echoes from the deep that tell us an extraordinary story. It is a story of a planet with a complex and dynamic inner life, a structure of distinct layers, each with its own incredible properties. Understanding this inner world is not just a matter of scientific curiosity, it is fundamental to understanding everything about our planet, from the magnetic field that protects us to the very ground beneath our feet. The story has taken a fascinating turn in recent years. We have long known the Earth's inner core spins, but new evidence suggests something truly remarkable is happening. It appears the core's rotation relative to the rest of the planet has slowed, perhaps even paused, and may now be reversing its direction in a slow, cyclical dance that takes decades to complete. This is not science fiction. It is the conclusion of painstaking research that pieces together clues from countless earthquakes recorded over many years. This revelation opens up a whole new set of questions about the forces at play deep within our world and how they connect to subtle changes we can observe right here on the surface. So, let us begin this journey together into the fiery center of our home. We will explore the majestic architecture of our planet, from the thin crust to the solid iron heart. We will meet the pioneering scientists who first mapped this unseen territory and learn about the clever methods they used. We will delve into the strange and wonderful physics that governs this hidden realm and uncover the story of the great spin reversal. It is a story that reminds us that even after millennia of living on this world, we are only just beginning to comprehend the full, magnificent complexity of the planet we call home. If you could slice the Earth in half like a giant piece of fruit, you would see that it is not a uniform ball of rock. Instead, it is made of several distinct and beautiful layers, each one different from the last. The part we know best is the crust, the outermost layer. It is incredibly thin compared to the rest of the planet, like the skin of an apple. This brittle shell is where we live, where our mountains rise and our oceans sit. It is broken into massive pieces called tectonic plates, which are constantly, slowly, drifting around, creating earthquakes and building mountain ranges over millions of years. It is the stage upon which the entire drama of life has unfolded. Just beneath the crust lies the largest layer of all, the mantle. This immense region makes up about 84% of Earth's volume. While we often think of it as solid rock, the mantle behaves more like an incredibly thick, slow-moving liquid over geological time. Imagine a river of treacle that moves only a few centimeters per year. This slow, churning motion, driven by heat rising from deeper within the planet, is the engine that moves the tectonic plates on the crust above. The mantle is a world of immense pressure and heat, a hidden powerhouse that shapes the surface of our planet in profound and powerful ways. Deeper still, we arrive at the core, which itself is split into two parts. First is the outer core, a vast, swirling ocean of liquid metal, primarily iron and nickel. The temperatures here are staggering, reaching thousands of degrees Celsius. It is the constant, turbulent motion within this liquid metal sea that generates Earth's magnetic field. This magnetic field extends far out into space, creating a protective bubble around our planet that shields us from harmful solar radiation. Without the dynamic liquid outer core, life on Earth might not be possible, as our atmosphere would have been stripped away by the solar wind long ago. It is a planetary dynamo of epic proportions. Finally, at the very center of it all, we find the inner core. Despite being even hotter than the outer core, with temperatures estimated to be around 6,000 degrees Celsius, as hot as the sun's surface, this layer is solid. The reason it is not liquid is due to the unbelievable pressure at the center of the Earth, which is so immense that it forces the iron atoms to lock into a solid, crystalline structure. This solid ball of iron, nearly the size of the Moon, is the planet's ultimate heat source. It is the mysterious, spinning heart of our world, and its behavior is the key to some of Earth's deepest and most fascinating secrets. The idea of a dense core deep inside the Earth is not entirely new. As far back as the 1890s, scientists like Emil Wiechert were pondering a simple but profound puzzle. They had calculated the Earth's average density and found it was much higher than the density of the rocks we find on the surface. The only way to explain this was if the planet's interior contained something incredibly heavy. Wiechert proposed that Earth must have a massive core made of iron to account for the missing mass. It was a brilliant piece of logical deduction, but at the time there was no way to prove it. The proof would have to wait for a new way of seeing inside the planet. That new way came from studying earthquakes. When an earthquake occurs, it releases a tremendous amount of energy that travels through the Earth in the form of waves. These are called seismic waves. In 1897, after a massive earthquake in India, a scientist named Richard Dixon Oldham was studying the recordings, or seismograms, from around the world. He noticed that some waves, which he called primary or P waves, seemed to slow down when they passed through the center of the Earth. He correctly concluded that this meant they were traveling through a different kind of material, a central core. It was the first piece of direct evidence that Wiechert's iron heart was real. The story got even more interesting as scientists studied other types of seismic waves. They observed another kind called secondary or S waves. A key property of S waves is that they cannot travel through liquids. They simply stop. Scientists noticed that S waves from an earthquake would travel through the mantle, but they would never appear on seismographs on the opposite side of the planet. There was a huge shadow zone where they were blocked. This led to the inescapable conclusion that the Earth's core must be liquid. For a time, it was believed the entire core was a molten sphere. But one final brilliant discovery was yet to come. That discovery was made in the 1930s by a Danish seismologist named Inger Lehmann. While studying the P-wave shadow zone, she noticed something peculiar. Faint P-waves were showing up where they shouldn't be. It was as if something at the very center was deflecting or bending some of the waves, sending them into the shadow. In a groundbreaking paper simply titled P, she proposed the only explanation that fit the data. The core had two parts. There was a liquid outer core, as others had discovered, but inside that was a solid inner core. Her meticulous analysis of these faint echoes gave us the final piece of the puzzle, revealing the four-layer structure of the Earth we know today. The inner core is truly the most extreme environment on our planet. It is a solid ball of mostly iron with some nickel suspended in the liquid outer core. Its size is immense, about 2,440 kilometers in diameter, which is roughly 70% of the Moon's diameter. The temperatures are almost beyond comprehension, reaching up to 6,000 degrees Celsius. This is as hot as the surface of the Sun, a furnace of primordial heat left over from the formation of our planet some 4.5 billion years ago, supplemented by heat from the decay of radioactive elements. This incredible heat is what drives the convection currents in the outer core and mantle, making the inner core the ultimate engine of our planet's geology. What is perhaps most mind-boggling is that despite this extreme heat, the inner core is solid. The reason lies in the crushing pressure at the center of the Earth. The weight of the entire planet, all the rock and liquid metal of the mantle and outer core, presses down on the center with a force more than 3.5 million times greater than the atmospheric pressure we experience on the surface. This immense pressure is so strong that it overcomes the thermal energy of the atoms and forces them to crystallize, locking them into a solid lattice structure. It is a perfect example of how materials can behave in completely unexpected ways under extreme conditions. One of the most fascinating properties of the inner core, discovered by scientists at Harvard University, is something called anisotropy. This is a scientific term that simply means an object has different properties in different directions. A good way to think about it is like the grain in a piece of wood. It is much easier to split a log along its grain than against it. Scientists found that seismic waves travel faster through the inner core when moving along a path parallel to the Earth's axis of rotation from pole to pole than when traveling along a path parallel to the equator. This gave us a crucial clue about the inner core's structure. This anisotropy suggests that the iron crystals making up the solid inner core are not arranged randomly. Instead, they are aligned like tiny metallic needles, all pointing in roughly the same direction. This large-scale crystalline structure is what creates the grain that allows seismic waves to travel faster one way than another. This alignment is not perfectly matched with the Earth's spin axis. It is tilted by a few degrees. And this slight tilt turned out to be an incredibly useful feature because it gave scientists a distinct marker they could track over time, allowing them to measure something once thought impossible, the rotation of the inner core itself. For a long time, scientists assumed that the whole Earth, crust, mantle, and core, spun together as one solid body, completing a single rotation every 24 hours. The idea that the inner core could be spinning independently was a radical one. Because the solid inner core is floating within the liquid outer core, it is not rigidly connected to the rest of the planet. In theory, it could spin at a different rate. The challenge was finding a way to prove it. The breakthrough came in 1996 from scientists at Columbia University who devised a brilliantly clever method to detect this separate motion using earthquakes as their stopwatch. Their technique relied on what they called earthquake doublets. These are pairs of earthquakes that occur in the exact same location, but many years apart. A specific region in the South Atlantic, the South Sandwich Islands, is a perfect source for these doublets. The scientists looked at seismic waves generated by these identical earthquakes, which traveled from the South Atlantic through the inner core and were recorded by a seismograph station in Alaska. The logic was simple. If the inner core was stationary relative to the mantle, the path the waves took would be identical each time, and the travel time would be exactly the same. However, what the researchers found was astonishing. When they compared the travel times for seismic waves from an earthquake in the 1960s to a nearly identical one in the 1990s, they discovered a small but measurable difference. The waves from the later earthquake arrived slightly faster. The best explanation for this was that the inner core had rotated slightly in the intervening decades. Because of its anisotropic crystal structure, the core's rotation had moved the fast axis of the iron crystals into a more direct line with the earthquake-to-station path. It was the first solid observational evidence that the inner core was spinning faster than the rest of the planet. This discovery painted a new and dynamic picture of our planet's interior. The inner core was not just a static lump of iron. It was a spinning world within a world, lapping the surface by about 1 degree of longitude per year. This differential rotation was thought to be driven by the powerful magnetic forces generated in the liquid outer core, which tug on the solid inner core and make it spin. For years, this model of a super-rotating core was the leading theory. But science is a process of constant refinement, and as more data became available, a more complex and even more interesting story began to emerge. Just as the scientific community was getting comfortable with the idea of a fast-spinning inner core, new research began to challenge the narrative. As seismologists continued to monitor earthquakes and analyze decades of data, some inconsistencies started to appear. In 2023, a study from researchers at Peking University made a startling announcement. After analyzing seismic waves that had passed through the core from the 1960s to the present day, they concluded that the inner core's faster rotation had not been constant. In fact, their data suggested that around the year 2009, the inner core's superrotation had nearly come to a halt relative to the mantle. This was a major plot twist in the story of the inner core. The researchers proposed that the core's spin wasn't a one-way race, but part of a long, slow cycle. They found evidence of a similar change in rotation that occurred back in the early 1970s, suggesting a pattern. Their theory was that the inner core oscillates back and forth, sometimes spinning slightly faster than the mantle, and at other times spinning slightly slower, essentially moving backward from our perspective on the surface. They estimated that this entire cycle of speeding up, slowing down and reversing takes roughly 70 years to complete. The core was not just spinning, it was dancing to a very slow rhythm. This idea was further supported by another study in early 2024 from the University of Southern California. This team analyzed waves from 121 repeating earthquakes in the South Sandwich Islands recorded between 1991 and 2023. Their findings confirmed the slowdown and provided strong evidence for the back-and-forth oscillation. According to their calculations, the inner core is now in a phase where it is lagging behind the mantle's rotation and is due to begin speeding up again soon. This cyclical motion is believed to be the result of a cosmic tug-of-war between two immense forces: the electromagnetic pull from the outer core trying to spin it, and the immense gravitational pull from dense, heavy structures in the lower mantle trying to hold it in place. So, what we are witnessing is not a permanent reversal in the way a car might go from drive to reverse. It is more like two dancers spinning together, where one sometimes gets slightly ahead and then falls slightly behind in a repeating pattern. The pause and slight backward motion are all part of a grand 70-year cycle. This discovery transforms our view of the Earth's deep interior from a relatively steady system to one of constant, subtle change. It reveals a delicate balance of forces at the heart of our world, a dynamic interplay that we are only just beginning to understand. How can we possibly know what is happening over 6,000 kilometers beneath our feet? The answer lies in the planet's own vibrations. We cannot drill to the core. The deepest hole ever made, the Kola Super Deep borehole, only scratched the surface, reaching just over 12 kilometers down, a mere 0.2% of the way to the center. Our only tools for exploring the deep interior are the seismic waves generated by earthquakes. Every time the Earth shudders, it sends out energy that pings through the planet like a medical ultrasound. A global network of highly sensitive instruments called seismographs acts as our planetary stethoscope, listening carefully to these vibrations as they arrive. There are different types of seismic waves, and their behavior is what tells us about the layers they travel through. P waves, or primary waves, are compression waves, like sound. They can travel through solids, liquids, and gases. When they pass from one layer to another, say from the solid mantle to the liquid outer core, they bend and change speed, a process called refraction. S waves, or secondary waves, are shear waves which move side to side. Their crucial property is that they cannot travel through liquids. By mapping where S waves are blocked, scientists were able to confirm the existence of the liquid outer core. To study the inner core's rotation, scientists need an even more precise technique. This is where the concept of earthquake doublets comes into play. By comparing the waveforms, the unique squiggly lines on a seismogram, from two earthquakes that occurred in the same spot years apart, scientists can look for tiny time differences. If the inner core has rotated, the path the wave takes through the core's anisotropic grain will change slightly, altering the travel time by a fraction of a second. It is an incredibly delicate measurement that requires decades of high-quality data and powerful computers to analyze. A newer method expands on this idea. Instead of looking for perfect doublets, researchers now use advanced algorithms to find matching waveforms from different earthquakes that occurred at different times. They are essentially searching through a vast library of seismic data to find moments when the inner core was in the exact same rotational position relative to the mantle and the seismograph station. This allows them to build a much more detailed timeline of the core's rotation, confirming the 70-year oscillation cycle with greater confidence. It is a testament to how modern computing power allows us to hear the faint whispers from our planet's heart with ever-increasing clarity. It may seem that a tiny change in the spin of a solid ball of iron 6,000 kilometers below us could not possibly have any effect on our lives. But the Earth is a deeply interconnected system, and this dance at the planet's core does appear to create subtle ripples that reach all the way to the surface. One of the most direct connections is with the length of a day. The Earth's rotation is not perfectly constant, and the length of a day can fluctuate by tiny amounts. Scientists have noticed a fascinating correlation. The 70-year oscillation of the inner core's rotation seems to line up with variations in the length of the day, on the order of thousandths of a second. This connection makes sense when you think about the conservation of angular momentum. The same principle that makes a spinning ice skater speed up when they pull their arms in. The Earth system as a whole, from the inner core to the atmosphere, tends to keep its total angular momentum constant. So, if the inner core slows down its spin slightly, the mantle and crust must speed up just a tiny bit to compensate, making our day infinitesimally shorter. Conversely, when the core speeds up, the day gets a fraction of a second longer. These changes are far too small for us to notice, but they are measurable with atomic clocks. The inner core's dance also appears to be linked to changes in Earth's powerful magnetic field. This field is generated by the churning liquid outer core, but the motion of the solid inner core within it likely has a subtle influence. The same 70-year cycle has been observed in some long-term fluctuations of the magnetic field's behavior. The gravitational coupling between the mantle and the inner core means that as the core oscillates, it could be tugging on the mantle above it, potentially influencing long-term geological processes like plate tectonics, though this link is still highly speculative and requires much more research. Furthermore, some studies have suggested correlations between this deep Earth cycle and long-term patterns in global mean temperature and sea level. It is crucial to be clear these effects are minuscule and are not the cause of modern global warming, which is unequivocally driven by human activity. However, these correlations suggest that the entire Earth system is coupled in ways we are only just beginning to appreciate. The slow heartbeat of the inner core seems to send faint pulses throughout the entire planet, a reminder that nothing in our world exists in complete isolation. The study of the Earth's core might feel like a distant and abstract field of science, but it is fundamental to who we are and where we live. Understanding the heart of our planet is essential for comprehending the processes that make Earth a habitable world. The core is the ultimate source of the heat that drives plate tectonics, the process that recycles our planet's crust, builds mountains, and shapes continents. Without this internal engine, Earth could have become a static, geologically dead planet, much like Mars or Mercury. The core is, in a very real sense, the reason our world is so dynamic and alive. Furthermore, the relationship between the inner and outer core is the key to our planet's magnetic shield. This invisible force field, generated by the liquid outer core, protects our atmosphere and all life on the surface from the constant bombardment of charged particles from the sun. Understanding how this dynamo works, how it is influenced by the inner core's rotation, and how it might change over geological time is crucial for predicting its future. The magnetic field has weakened and flipped its polarity many times in Earth's history, and knowing more about the core helps us model and prepare for such future events, however distant they may be. This research also teaches us a profound lesson about our place in the universe. It showcases the incredible power of the scientific method, our ability to use indirect evidence like the faint echoes of earthquakes to map a world that is completely inaccessible. It is a story of human curiosity and ingenuity, of building upon the discoveries of previous generations to piece together a puzzle of immense scale and complexity. Each new discovery, like the oscillation of the inner core, does not just provide answers, it opens up a whole new landscape of questions, pushing us to refine our theories and listen even more closely to what the planet is telling us. Ultimately, by studying the very heart of our world, we learn more about the intricate and delicate connections that make up the Earth system. From the spin of the core affecting the length of our day, to the heat that drives the continents, everything is linked. This research inspires a sense of wonder and humility. It reminds us that we live on the thin, fragile surface of an incredibly complex and powerful planet, and by continuing to listen to its deepest rumbles and its faintest whispers, we gain a deeper appreciation for the magnificent world we call home and the importance of protecting it.